Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Once awesome 896 Henri Becquerel on the invisible rays emitted by phosphorescent substances. In the annals of scientific discovery, certain moments stand apart, not only for their groundbreaking nature, but also for the elegant simplicity with which they appended established paradigms. Such a moment arrived in 1896, when Henri Becquerel, a name now synonymous with radioactivity, stumbled upon an entirely new form of radiation, forever altering our understanding of the atom and the nature of energy. The central puzzle concerned the seemingly inexplicable emission of penetrating radiation from uranium salts, a phenomenon initially misconstrued as a derivative of phosphorescence. Becquerel's investigation, meticulously documented on the invisible rays emitted by phosphorescent substances, began with an experimental setup that, at first glance, appeared straightforward. He sought to build upon the recent excitement surrounding Wilhelm Conrad Röntgen's discovery of X-rays and their purported link to phosphorescence. Becquerel's initial hypothesis, typical of the time, linked the emission of these new rays to the absorption of sunlight by phosphorescent materials. His experimental design cleverly leveraged this assumption. He employed uranium salts, known to exhibit phosphorescence, and placed them on top of photographic plates. The photographic plates, carefully wrapped in black paper to shield them from any external light, served as detectors for the hypothesized X-rays, which were thought to be able to penetrate the opaque covering. The experimental design rested on the assumption the sunlight would energize the uranium salt, which would then emit the penetrating rays, fogging the early results, however, quickly shattered this initial premise. Becquerel observed that the photographic plates, shielded from light, were exposed. This was a baffling observation. The plates were fogged. The fact that the uranium salts continued to emit these mysterious rays, even when kept in complete darkness, presented a fundamental challenge to the prevailing theory. The sun's energy and the ensuing phosphorescence it triggered were not the source. Becquerel, through his dogged experimentation, uncovered an entirely independent phenomenon. Becquerel's meticulous approach allowed him to make specific claims. The radiation emitted by the uranium salts was independent of sunlight exposure, a critical divergence from the expected behavior of phosphorescent materials. This independence was a cornerstone of his conclusions. Further experiments using different uranium compounds revealed that the intensity of the radiation was proportional to the uranium content, offering a direct link between the substance and its radiative properties. The substance itself seemed to be the source. Furthermore, the radiation, unlike visible or ultraviolet light, could penetrate various opaque materials, including black paper, aluminum, and even thin sheets of glass. This penetrating ability was one of the radiation's identifying features. The importance of Becquerel's discovery must be understood within the broader context. The scientific community buzzed with the recent discovery of X-rays. Röntgen's work, published in late 1895, sent ripples through the scientific community. These rays could penetrate opaque objects, and they caused some materials to fluoresce. Becquerel, a distinguished physicist, pursued his inquiry within this framework, attempting to find a connection between phosphorescence, X-rays, and this new, mysterious radiation. He had initially presumed that sunlight, in its interaction with the uranium salt, triggered the emission of X-rays. His experiments were designed to test this proposition. The paper under examination begins to detail the specific methodology, the impact, and the continuing legacy of Becquerel's discovery. The following sections will provide a detailed analysis of Becquerel's experimental methodology, showing how his carefully designed approach, involving photographic plates and various uranium compounds, enabled the identification of a new radiation type. The properties of this new radiation will be presented alongside its capacity to penetrate various materials, indicating a fundamental shift in understanding of energy and matter. The profound implications of these findings will be explored alongside its initial influences, its immediate impact, his long-term legacy of Becquerel's groundbreaking. Delving into Becquerel's experimental methodology, one observes the meticulousness that defined his scientific prowess. Inspired, in part, by Röntgen's discovery of X-rays the previous year, Becquerel initially considered a connection. He surmised that phosphorescent uranium salts, when exposed to sunlight, would emit X-rays. Röntgen's work, while groundbreaking, offered a conceptual framework for Becquerel's investigations, influencing both his experimental design and early hypotheses. This established a direct influence from Röntgen's work to Becquerel's work. Becquerel used photographic plates wrapped in black paper, a standard practice for detecting X-rays. He exposed these plates to various uranium compounds, including potassium uranyl sulfate, His initial experiments involved placing the uranium salt on the wrapped plates and exposing them to sunlight. He anticipated that the sunlight would trigger the emission of X-rays, which, in turn, would expose the photographic plates, providing the evidence he sought to confirm his hypothesis. The crux of his breakthrough emerged from a series of serendipitous observations and rigorous experimentation. Initially, results were inconclusive, however. The cloudy skies of February 1896 intervened, with the uranium compound and photographic plates prepared, but under grey skies. Becquerel stored his apparatus away in a drawer. Several days later, he developed the photographic plates, expecting minimal results, but instead he found a strong, unexpected image. This discovery was pivotal. It revealed that the uranium salt, without sunlight exposure, had still produced a clear image on the photographic plates. Moreover, the intensity of the image seemed the same as the plates previously exposed to sunlight. Becquerel meticulously repeated the experiment, varying both the uranium compounds and the materials between the uranium salt and the photographic plate. He methodically demonstrated that the emission was independent of sunlight. The emission relied on an intrinsic property of the uranium itself. He proved this through several crucial experiments. He utilized different uranium salts, including metallic uranium, and obtained similar results, confirming the radiation's origin within the uranium atom. Further, the radiation penetrated various materials, including thick black paper and thin metal sheets. This ability indicated a penetrating power exceeding that of visible light, indicating the new radiation type. He also demonstrated that the intensity of the radiation correlated with the concentration of uranium in the compound. The more uranium present, the stronger the effect on the photographic plate. The properties of this new radiation were intriguing. It was invisible, capable of penetrating opaque materials, and emanated from uranium regardless of external factors like sunlight. This radiation possessed properties distinctly different from X-rays. X-rays were generated by the interaction of cathode rays with a target material. Becquerel's radiation arose spontaneously. The implications of Becquerel's findings were profound. His work fundamentally challenged the established understanding of energy and matter. It demonstrated that atoms, previously considered indivisible, possessed internal energy. This energy could be emitted in the form of radiation, a concept revolutionary for the time. His work laid the groundwork for understanding the atom's structure. Becquerel's revelation directly influenced Marie and Pierre Curie. They immediately recognized the significance of his findings. They embarked on their own research, expanding upon Becquerel's work. They later discovered additional radioactive elements, polonium and radium, further solidifying his initial impact. Their work built directly upon Becquerel's discovery. Becquerel's discovery immediately captivated the scientific community. His findings were presented to the Académie des Sciences in Paris, sparking immediate interest and investigation. Scientists globally began exploring the phenomenon, leading to a rapid expansion of research. The earlier applications of his discovery were initially limited. The immediate impact was primarily scientific, focusing on understanding the nature of the radiation. However, the discovery quickly paved the way for medical and industrial applications. The radiation's ability to penetrate materials, similar to X-rays, soon found a place in medical imaging. The long-term legacy of Becquerel's work is monumental. His discovery inaugurated the field of nuclear physics. It provided the initial evidence of radioactive decay, a process where unstable atomic nuclei emit particles and energy to become more stable. This led to the development of atomic theory. His work helped to understand the structure of the atom, showing that it was composed of smaller particles. The research provided the foundation for the atomic age. His work continues to resonate in the field of medicine, where radiation therapy became a powerful tool in cancer treatment. Becquerel's exploration of the initially mysterious process was a catalyst. It initiated a scientific revolution, permanently altering our understanding of the universe. His work served as a pivotal moment. It transformed science's trajectory. This created a profound shift in the scientific community. Becquerel's findings, arising from a chance observation, unveiled an entirely new realm of physics. The ongoing influence of his work on scientific inquiry is undeniable.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.